Welcome to Week 7, Lecture 3, Correlation and Regression. So let's go over an example. A researcher has developed a new test of self-esteem. To evaluate the reliability of the test, the researcher obtains a sample of 5 participants. Each individual takes a test on Monday morning and then returns 2 weeks later to take the test again. In general, it's useful to plot the data in a scatter plot and make preliminary estimates of the correlation. By looking at this scatter plot, it appears that there is a very good, not necessarily perfect, positive correlation. You would expect an approximate value of R being somewhere between 0.8 and 0.9. Let's go ahead and start our hypothesis testing. Step 1 of the hypothesis test is to state your null and alternative hypotheses. So let's go ahead and do that. Our null hypothesis states that the population correlation, or rho, is equal to 0. So in other words, there is no population correlation. In terms of the experiment that we're interested in, the new self-esteem measure is not reliable. Our alternative hypothesis is stated as rho is not equal to 0. In other words, there is a real correlation. In terms of our test, we would state the new self-esteem measure is reliable. On to step 2, where we set our criteria. We set our value of alpha equals to 0.05. And we can go directly to the table because actually this table doesn't require degrees of freedom. We just need to know the n, how many people we have in our study, and our alpha level. Well, our alpha level is 0.5, so we're just interested in this first column. And our n is a value of 5. So our critical value is 0.878. So we go ahead and write our critical value, and remember it's plus or minus 0.878. So now we go ahead and we compute our test statistic. Again, our formula, or the formula that I'm using, is the same as the formula in the book. It's just that I like to use a little simplified version in terms of the letters, but computations are identical. If you don't recall, go back to lecture 1 where I went over this. So to compute the value for the Pearson correlation, we need to find the values for our sum of products, our sums of squares x, and our sums of squares y. And the formulas that I went over in the first day are as follows for the sums of products, the sums of squares x, and the sums of squared y's. Another way we can refer to these formulas are as computational formulas. These are the same formulas that we used in the past, and we made the distinction between computational formulas. There is an alternative formula for these, and we talked about these formulas at the very beginning of this term. And that is, these formulas are the definitional formulas. And if you think way back to I'm going to say probably, well, I can't even say off the top of my head because it's been a while, but if we think back to the beginning of the term, we actually used the definitional formulas at the beginning. Now, if you have to compute your R by hand, I strongly recommend that you use definitional formulas, and you'll see why it actually comes out quite easily. So let's go ahead and do that. We're going to take the following data sets, and we're going to go ahead and compute the mean for the x variable and for the y variable. And so we get a mean of 6 for the x variable and a mean of 2 for the y variable. Our next step is to find the x value minus the mean of x. And so let's go ahead and do that. So 0 minus 6 is negative 6. 10 minus 6 is 4. 4 minus 6 is negative 2. 8 minus 6 is 2. And 8 minus 6. And 8 minus 6 is positive 2. And so if we went ahead and added up this column, what we would get is a value of 0, and that shouldn't come as a surprise. If you think way back to the beginning of the term when we first learned how to compute sums of squares, if we summed all the deviations, we would get a value of 0. And for this reason, we need to take the deviations and square them and then sum them. So let's go ahead and do that. And so now we have a column where we take the value of x subtracted by the mean and we square it. And so 6 squared is 36, 4 squared is 16, negative 2 squared is 4, 2 squared is 4, and finally 2 squared is 4. And now we go ahead and add up these values, and we get a sum of squares x that is equal to 64. Now we do the same thing for the value of x. Now we do the same thing for the y variable. We simply take every individual value of y and subtract it from the mean of the total of the y variables. So we go ahead and we take 0 and we go ahead and we take the value of 1 and we subtract 2, and that gives us a value of negative 1. We take the value of 3 and subtract 2, and that gives us a value of positive 1. 1 minus 2 is negative 1, 2 minus 2 is 0, and 3 minus 2 is 1. And again, if we add up these values, our sum of deviations would be 0. Therefore, we need to square these. And so to get our sums of squares, we simply need to take every deviation, square it, and then sum it. 1 squared is 1. Positive 1 squared is 1. Negative 1 squared is 1. 0 squared is 0. And positive 1 squared is 1. So now we simply add up these values to get the sum of squares y. And the value for the sum of squares y is 4. That's great. So now we have we have 2 of the 3 values that we need to compute our r. Now, one of the reasons why I find this way a little bit easier is because finally, to get our sum square products, we simply need to take the multiplication of the deviation for the x variable by the deviation for the y variable. So we simply take the values in this column and multiply it by the values in this column. So negative 6 times negative 1 gives us a value of 6. 4 multiplied by 1 is 4. Negative 2 multiplied by negative 1 is 2. 0 times 2 is 0. And 2 times 1 is 2. So now we simply need to add this column so that we can get our value for the sum of products. And our value for the sums of products is 14. We can now use these values to compute the Pearson correlation. So the Pearson correlation is simply as follows. The sum of products divided by the square root of the sums of squares x and the sums of squares y. So we go ahead and plug the values, and we simply solve for them, which is a value of 0.875 for the value of r. So now we go ahead and graph the example, and our r is 0.875. And this correlation is consistent with the pattern that is shown. If you think back to the beginning of the example, we kind of predicted the correlation is strong positive correlation somewhere around 0.8 or 0.9. So this indicates that the points are clustered around the line that slopes up to the right. So if you were to draw a line here, you could see that it kind of follows the path of the slope. It indicates that the points are also very tightly clustered and close to the line. Now let's go on to step 4 in making our decision. So now we simply compare our obtained value for r of 8.75 to our critical value of 8.78. And what we find is that our r obtained is less than our critical value. So in other words, our r obtained is not in the critical region. Thus, we failed to reject the null hypothesis. The question that we might ask ourselves is, how reliable is this new test of self-esteem? And even though we failed to reject the null hypothesis, we can look at our value of r squared to give us an idea of how reliable the test is. So r squared is 0.7656. In other words, the new test of self-esteem is 76% reliable. I want to stop here and just say something about this. The value of r equals 0.875 is a pretty strong relationship. Having something being 76% reliable is actually pretty reliable. So right now, some bells should be going off in your head saying, wait a minute, how can we fail to reject the null under these circumstances? Because it seems like there is a real relationship here. Well, the answer is yes, there is a relationship here. One, you can tell because the critical and the obtained values are very close together. And if we were to increase our sample size size, even by one subject, we would actually get a response where we would reject the null hypothesis. So this is also a good example of how you really need large sample sizes to get accurate results. Because the sample size was very small, I think that we got an error here. Now, the reason our sample size is small is for the purposes of our class. I don't want to do 30 plus data points when we're doing our sums of squares by hand. And so that is why I generally like to keep our sample sizes, for example, small. But I just wanted to point that out for you, especially for those of you that have been paying attention and realize that this is a pretty strong relationship, even though we failed to reject the null. Now I'd like to switch gears a little bit and talk about the regression line. In this section, we will find an equation for a straight line that best fits the paired of sample data. That equation describes the relationship between the two variables. The best fitting straight line is called the regression line, and its equation is called the regression equation. We introduced the Pearson correlation as a technique for describing and measuring the linear relationship between two variables. We can graph the regression equation onto the scatter plot to visually determine how well it fits the data. In other words, we have drawn a line through the middle of the data points. This line serves several purposes. First, the line makes the relationship between the new self-esteem measures easier to see. Next, the line identifies the center or the central tendency of the relationship, just as the mean describes the central tendency for a set of scores. Thus, the line provides a simplified description of the relationship. Finally, the line can be used for prediction. The line establishes precise relationship between each x value and each corresponding y value. Our goal in this section is to develop a procedure that identifies and defines a straight line that provides the best fit for a specific set of data. You should realize that this straight line does not have to be drawn on the graph. It can be presented in a simple equation. Thus, our goal is to find the equation for the line that best describes the relationship for the set of x and y data. Linear equations. In general, a linear relationship between two variables, x and y, can be expressed by the regression equation, often referred to as follows. Y hat is equal to b sub 1 multiplied by x plus b sub 0 or b sub naught. In this example, x is also referred to as the explanatory variable or the predictor variable or the independent variable. Y hat is also referred to as the response variable or the dependent variable, what we're measuring. B sub 1 is considered the slope line, and B sub naught or B sub 0 is considered the intercept. And this is not to be confused with the slope-intercept form of a typical equation of a straight line, which is y equals mb plus x, where the 2 points in that straight line completely determine the straight line. And the resulting straight line is called the regression line. The goal for regression is to find the best fitting straight line for a set of data. To accomplish this goal, however, it is first necessary to define precisely what is meant by best fit. Given a data set, it is possible to draw a lot of different straight lines that appear to pass through the center of the data points. For example, this line seems to pass through the center, so does this. Each of these lines can be defined by a linear equation. Each individual line has its own unique values for the slope and intercept. The problem is, however, not finding a line that passes closest through these, but rather finding a specific line that provides the best fit for the actual data points. In other words, we want to find the line where y hat equals b sub 1 plus x plus b 0. And to do this, we use the least square solution. In other words, to determine how well a line fits the data points, we must first define mathematically the distance between the line and each data point. The value on the line is called the predicted value, or the y-hat, and y-hat is represented on the line. The actual point is referred to as x. The distance between this predicted value and the actual value in the data is a type of error called a residual, and it is determined by the distance between y and y-hat. So in other words, the distance, or the residual, is simply taking the value of y, the value that we obtain, and subtracting the value of the residual, the value of the predicted y, or y-hat. Notice that we are simply measuring the vertical distance between the actual data point and the predicted point on the line. Because some of the distances will be positive and some of the differences will be negative, the next step is to square each distance in order to obtain a uniformly positive measure of this residual error. So finally, to determine the total error between the line and the actual data, we sum the squared errors for all the data points. The resulting measure of the overall squared error between the line and the data is also referred to as the total squared error. So it's simply every error, or every little line distance we get here, squared and then summed. So now we can find the best fitting line as the one that has the smallest total squared error. For obvious reasons, the resulting line is commonly referred to as the least squared error solution. Now let's go ahead and talk about the regression formulas. Now we've introduced the regression formula earlier in this lecture. And now I want to go ahead and break these down in terms of the value and how we compute them. So for the slope, or to find the solution for the slope, we simply take the value of the sum of products and we divide it by the sums of squares. To find the solution for the intercept, or the value for the intercept, what we need to do is we take the mean of the y variable and we subtract it from the slope multiplied by the mean for the x variable. So if we think back to our example, we take this formula and we go back to the example that we did at the beginning of the lecture and we simply solve the regression equation. So for the slope, we need to take the sum products and divide it by the sums of squares. And here are the values that we need. So we simply take the value of 14 and divide it by 64. And once we do, and so for the slope, we get a value of 0.219. Now let's go ahead and place this value into the equation. Okay, and now we need to solve for the intercept. And so the formula for the intercept is as follows, and we mentioned it earlier. It's simply the mean of the y variable, which we have down here, subtracted by the slope, which we have over here, multiplied by the mean of the x variable, which we have over here. So we go ahead and plug those values in, and we just solve for the equation. And if we do that, we get a value of 0.686, and we go ahead and take that value and plug it back into the equation, and we have a regression equation. So now we have our regression equation. We can test and see how accurate it is. So if we had a value of 10 and we placed it into that regression equation, our predicted value would be 2.876. And if we look at our data, we do have a value of 10 for the x variable, and the corresponding y value for that variable is 3. And based on our predicted y, we can tell that there is a very little error between what we predicted and the actual score obtained. Regression equations are often used for predicting values of one variable given some specific value of another variable. There are several cautions that should be considered whenever you're interpreting the predicted values. Use the regression equation for predicting only if the graph of the regression line on the scatter plot confirms that the regression line fits the points reasonably well. In other words, only if error is small. The prediction value is not perfect. In general, there always will be some error between the predicted values on the line and the actual data. Although there is a small amount of error that will vary from point to point, on average, the errors will be directly related to the magnitude of the correlation. With the correlation near 1 or plus or minus 1, we have the data points will generally be close to the line, indicating small amount of error. With the correlation gets near 0, the magnitude of the error will increase. The statistical procedure for measuring error is described in the following section. Use the regression equation for predictions only if the linear correlation coefficient indicates that there is a linear correlation between two variables. In other words, if you're not finding a significant Pearson correlation, then you cannot use the regression equation to make predictions. Also, use the regression equation for predictions only if the data do not go much beyond the scope of the available sample data. The regression equation should not be used for making predictions for X values that fall outside the range of values covered in the original data set. The regression equation should not be used to make predictions for X values that fall outside the range of the values covered in the original data set. For example, if the X values range from X equal to 3 to X equal to 7, the regression equation was calculated for the best fitting line within that range. Thus, it should not be used to predict Y values that correspond to X values less than 3 or greater than 7. Lastly, if the regression equation does not appear to be useful for making predictions, the best predicted value of the variable is a point estimate, which is its sample mean. Finally, let's talk a little bit about the standard error of estimate. It is possible to determine the best fitting equation for any data set by simply using the formulas already presented. However, it should be clear that the accuracy of this prediction depends on how well the points on the line correspond to the actual data points. That is, the amount of error between the predicted values and the actual score values. To measure the precision of the regression equation, it is customary to compute the standard error of estimate. The standard error of estimate gives a measure of the standard distance between the regression line and the actual data points. In other words, the standard error of estimate is a measure of the difference or distances between the observed sample Y values and the predicted values of Y hat that are obtained using the regression equation. We can define To calculate the standard error of estimate, we simply take the sum of the squares error and divide it by the degrees of freedom, and we find the square root. Conceptually, the standard error of estimate is very much like the standard deviation. If you think back to the formula for the standard deviation, it's the sum of the squares over the degrees of freedom, and then we find the square root. Both provide a measure of standard distance. Also note that the calculation of the standard error estimate is very similar to the calculation of the standard deviation. To calculate the standard error of estimate, we need to first find the sum of squared deviations. This sum of squared deviations is often called sums of squares error because it measures the sum of squared error distance or errors between the actual data and the predicted values. And if you think back to the regression line that I drew and the distances, we are simply taking the actual score and subtracting from the score the predicted score or the score that's on the line. We're squaring it and then we're adding up all those distances. And then we divide that by the degrees of freedom. And if you think back, degrees of freedom for when we're talking about correlations is simply n minus 2. And just by looking at this, you can see that the smaller the standard error of estimate, the larger the correlation between x and y. So the smaller your error, the stronger the relationship between your variables. Well, thank you so much for listening to this lecture. I know it was a little bit on the long side, or at least a little bit tedious, but hopefully it makes sense. And the next and final lecture for this whole term will be an example of how to use correlation and regression. Just a summary of all the things that we've done so far in this week. So thank you so much, and you guys have a good evening.